In a recent study conducted by researchers at Tsinghua University, the Purple Mountain Observatory, and Peking University, a groundbreaking approach to detecting dark photons, prominent dark matter candidates, has been proposed. Dark matter, as we know, is a perplexing component of the universe that does not interact with light or electromagnetic radiation in the same way ordinary matter does. This property presents a significant challenge when it comes to directly detecting dark matter using conventional telescopes or imaging technologies. You see, ordinary matter interacts with light through various processes. It can emit light, absorb light when it passes through it, or reflect light when it strikes its surface. These interactions allow us to observe and study ordinary matter through telescopes that detect electromagnetic radiation, such as visible light, X-rays, or radio waves. However, dark matter does not engage in these interactions. It does not emit, absorb, or reflect light, rendering it effectively invisible to traditional observation techniques. This poses a conundrum for astrophysicists and has prompted them to explore alternative methods to detect this elusive form of matter. To understand why dark matter doesn't interact with light, we need to delve into its fundamental nature. Dark matter is believed to be composed of particles that are distinct from the particles making up ordinary matter, such as protons, neutrons, and electrons. These hypothetical dark matter particles, whatever they may be, possess unique properties that make them dark in terms of their interactions with light. The absence of direct interactions between dark matter and electromagnetic radiation has led researchers to devise innovative approaches to detect it. These methods involve seeking indirect signals or studying the gravitational effects of dark matter on visible matter. The search for direct detection techniques remains a key goal in our quest to unravel the mysteries of dark matter. In recent years, researchers have been exploring the possibility that dark photons, hypothetical particles analogous to ordinary photons but associated with a hidden sector of physics, could be a promising candidate for dark matter. Dark photons, if they exist, would carry a force in dark matter, much like photons carry the electromagnetic force in ordinary matter. This has prompted scientists to investigate whether dark photons could be directly detected using advanced instruments like radio telescopes. The concept of dark photons as potential dark matter candidates. Dark photons are hypothetical particles that have captured the interest of scientists exploring the nature of dark matter. They are envisioned as analogs to ordinary photons, which are particles of light that mediate the electromagnetic force in ordinary matter. Similar to how ordinary photons interact with charged particles and electromagnetic fields, dark photons would carry a force in dark matter. This force would be specific to the hidden sector associated with dark matter. Just as ordinary photons transmit electromagnetic interactions between charged particles, dark photons could potentially mediate interactions between particles in the hidden sector. However, there is a crucial distinction between dark photons and ordinary photons. Dark photons would interact very weakly with ordinary matter and electromagnetic radiation. This weak interaction makes it challenging to directly detect dark photons using conventional observation methods and instruments that rely on the detection of electromagnetic radiation. The weak interaction arises from the unique properties of dark matter and the hidden sector it is believed to inhabit. Dark matter is hypothesized to consist of particles that do not carry electric charge and have minimal interactions with ordinary matter. Consequently, dark photons, if they exist, would not readily couple to charged particles in the visible sector, leading to their elusive nature. The weak interaction between dark photons and ordinary matter presents a significant obstacle to their direct detection. Conventional telescopes primarily rely on the detection of electromagnetic radiation, which dark photons do not readily emit, absorb, or reflect. This limitation has spurred scientists to explore alternative detection methods that can overcome the challenge posed by the weak coupling between dark photons and ordinary matter. The researchers from Tsinghua University, the Purple Mountain Observatory, and Peking University embarked on a groundbreaking study to investigate the direct detection of dark photons using radio telescopes. They proposed a unique approach that leverages the capabilities of radio telescopes to induce and detect electromagnetic electromagnetic signals associated with dark photons. Their method revolves around utilizing the free electrons present in a dish telescope to induce electromagnetic signals that may be generated by the presence of dark photons. To understand this, let's delve into the technical details. In a radio telescope, the dish-shaped reflector collects radio waves from space and focuses them onto a receiver. The receiver then detects and measures the signals. In the case of detecting dark photons, the researchers envisioned that the free electrons within the telescope structure could be excited by the presence of dark photons, leading to the emission of normal photons. By inducing these electromagnetic signals through the excitation of free electrons, the researchers aimed to detect the telltale signatures of dark photons. This approach allows for the utilization of existing radio telescopes, such as the 500-meter aperture spherical radio telescope, FAST, in China, to search for these elusive signals. However, the non-relativistic nature of dark matter posed a challenge in the detection process. The shape of traditional dished radio telescopes, including FAST, is parabolic, with the receiver placed at the point of focus. This configuration means that the electromagnetic signals induced by dark photons would not concentrate at the receiver, hindering their detection. Initially, this limitation seemed to impede the feasibility of their proposed method. However, an important breakthrough came when the researchers discovered a solution. They realized that the receiver in radio telescopes like FAST is not fixed but movable. It can be positioned at different locations within the telescope structure, allowing for the collection of electromagnetic signals from various points. This mobility of the receiver opened up new possibilities. Although the dark photon-induced signals do not concentrate directly at the receiver, the electromagnetic field resulting from these signals forms a distribution on top of the telescope's dish. This distribution can be accurately calculated theoretically, providing a means to compare the observed signals with the predicted distribution. By analyzing and comparing the signals collected by the movable receiver with the theoretical distribution, the researchers could enhance the sensitivity of the telescope to detect dark photon-induced signals. This remarkable breakthrough demonstrates the potential of radio telescopes in directly detecting dark photons and contributes to the ongoing search for dark matter. The researchers made some remarkable discoveries that opened up exciting possibilities for the detection of dark photons. Although the shape of existing dished radio telescopes like FAST posed a hurdle due to the non-relativistic nature of dark matter, the movable receiver within these telescopes proved to be a crucial element in their method. The researchers performed theoretical calculations and analyses to assess the sensitivity of the FAST telescope in detecting dark photon-induced signals. To their surprise, even without considering the distribution of the induced signals, they found that the sensitivity of the telescope exceeded previous constraints. This groundbreaking discovery implies that the FAST telescope has the potential to detect dark matter composed of dark photons within the appropriate mass range. By surpassing the constraints set by previous observations, the researchers have demonstrated the capability of radio telescopes to make significant advancements in the search for dark matter. The sensitivity of a telescope is a crucial factor in detecting faint signals. In the case of dark photons, their weak interaction with ordinary matter requires highly sensitive instruments. The fact that the sensitivity of the FAST telescope alone already exceeds previous constraints is a testament to its extraordinary capabilities. This discovery not only reinforces the potential of the FAST telescope, but also indicates that radio telescopes, in general, can play a pivotal role in the direct detection of dark photons and, consequently, dark matter. It opens up new avenues for exploration and propels the ongoing quest to unravel the mysteries surrounding dark matter. In addition to the FAST telescope, the researchers also analyzed observation data from the Loeffler and Meerkat telescopes. Their calculations demonstrated that these telescopes, equipped with interferometry technology, have the potential to detect dark photon-induced signals as well. This expands the scope of the study and highlights the broader applicability of their method. The researchers didn't confine their work to theoretical calculations alone. They went a step further by analyzing observation data collected by the FAST radio telescope, which is located in the Guizhou region of China. This allowed them to place stringent bounds on the model in the 1 to 1.5 GHz frequency range, further validating the potential of their method. Moreover, the researchers explored the future prospects of dark photon detection by investigating the sensitivity of other radio telescopes, such as Loeffler Low-Frequency Array, and ska, square kilometer array. Through their calculations, they determined that these telescopes also have the potential to detect dark photon dark matter. LOFR, known for its sensitivity at low frequencies, and the future ska, designed to be the world's largest radio telescope, hold promise for expanding our understanding of dark photon dark matter. The non-relativistic nature of dark photons allows for the utilization of interferometry technology, which can enhance the sensitivity of these telescopes even further. By analyzing data from these telescopes, the researchers aim to validate their theoretical predictions and detect the elusive signals associated with dark photon dark matter. This experimental confirmation would provide crucial evidence for the existence of dark photons and their role as a component of dark matter. This groundbreaking research opens up new horizons in the field of radio astronomy. The direct detection of dark photons using radio telescopes has the potential to revolutionize our understanding of dark matter and shed light on the invisible components that shape our universe. The researchers plan to continue their investigations. They intend to search for dark photon dark matter signals in the data collected by telescopes like LOFR and ska, exploring a wider frequency range and expanding the scope of their discoveries. Additionally, they aim to apply their methodology to search for other ultralight dark matter candidates, including axions. These ambitious endeavors demonstrate the ongoing efforts to push the boundaries of knowledge and unravel the mysteries of the cosmos. Through the fusion of theoretical calculations, observational data analysis, and innovative methodologies, scientists are inching closer to a breakthrough in understanding dark matter and the fundamental nature of the universe. It is clear that we are on the brink of an exciting era in dark matter research. The innovative approach proposed by the researchers offers hope in unraveling the mysteries of our universe's hidden realms. With each step forward, we come closer to understanding the invisible forces that shape the cosmos. Thank you for joining us today. Don't forget to like, subscribe, and share this video. And as always, keep exploring and questioning the wonders of our universe.